Hello everyone, good afternoon. My name is Jimmy Fong, so I'm the head of the Division of Environment. Today I have the honor to introduce Professor Richard Flagan, our IAS visiting professor. Professor Flagan just arrived last Saturday, so he may still suffer from a little bit of jet lag, but he will stay here until May 6th. So other than today's seminar, he will run two more workshops. One is on aerosol instruments, another one on scientific writings, and we'll make more announcement later on this week or early next week. And Professor Flagan is Executive Officer of Chemical Engineering in Caltech. He's also the Professor of Environmental Science and Engineering. So he wearing two hats, like many of us here. His research focus is on aerosols and includes study of secondary organic aerosol in the atmosphere, of biological particles such as pollens and their health impact. And if you were here about a couple of years ago, and Professor Flagan was here, give us a seminar on pollen and their health impact. At the center of his research is on the development of the method for the physical, chemical, and biochemical characterization of aerosol particle ranging from particles as small as 1 nanometers diameter to pollen grains that exceed 100 microns in size. He also applied methods derived from aerosol science to the study of phase transition in materials and the development of separation technologies. Professor Flagan has published a lot of scientific papers. Altogether is something in the order of 340. And if anyone in the field of air pollution, you must have read his textbook on fundamentals of air pollution engineering. And he also holds about 20 patents. And above all, of course, he has won numerous awards and honors, just to name a few. He was elected to be the U.S. National Academy of Engineering in 2010. He got the American Chemical Society Award for Creative Advances in Environmental Science and Technology in 2007. And today's his seminar title is in The Recurring Challenge of Particulate in Air Pollution. Without further ado, I will leave the floor to Professor Flagan.
Thank you very much, Jimmy. It's a delight to be back here. I've lectured in this room once, or actually twice before, and had a very nice brief visit. This time I will be here a bit longer, and I look forward to talking with a lot of you at your convenience. Since I'll be here for several weeks, there should be plenty of opportunity. I'll talk today about a problem that is very apparent in this part of the world, very hard to miss. That is particulate air pollution. This is not a new problem. Would anyone care to guess when the first law was written about air pollution? Anyone hazard a guess? Let me make it easy. In what century? It was in the 14th century. And it was very simple. This is the first one I know of. There may be others. But London was having a very severe air pollution problem at the time. And there was a law written. They got tired of not being able to breathe when Parliament would meet. So there was a very simple law. Anyone who would burn coal when Parliament was in session would suffer the loss of his head. Very simple, very direct. There are no records, however, of it ever being enforced. Air pollution episodes have happened again and again throughout history. We are seeing a time when they are becoming very apparent once again. The last period when the level of intensity that we're seeing coming out of places like Beijing and Delhi today was in the mid-20th century. I'll show you some pictures from that. We'll start off just looking at a couple of them. There was what was called the Big Smoke. This occurred in December of 1952 in London. It was an extremely intense air pollution episode. If you look at the headlines in the newspapers in that era, where you see pictures, except for the buildings, it could be any of a number of megacities today that were suffering this. If you look at the headlines from the period, third day of a London particular, interesting word for it, they declared it as worse than the 1866 cholera epidemic, which was one of the worst epidemics that they'd had in 100 years in London. And it was killing more people. It was so dark that they actually had policemen walking in front of buses with lanterns, both so that the bus wouldn't get lost, but also so that it wouldn't run into anyone. The effects of this pollution were extreme. Here's a plot showing some index that they had for smoke, and these are qualitative indices. They didn't have the quantitative measurement instruments we have today, but they had this very intense smoke episode occurring over a period of about 5 days. And here's the death rate. And the death rate went way above the background rate for that time of year. It increased dramatically. It increased to the point that in the 5 days of the air pollution episode, something like 4,000 people died beyond the number that would normally die in that period. And over the next few weeks, another 8,000 people died that were attributed to this air pollution episode. So it killed, in one episode, on order of 12,000 people. And this is a question that we must ask about what's going on today. How many people are being killed? How many people are being made ill? How many people are being hurt by these extreme episodes that we're experiencing today? Now, this was not the only air pollution of that era. In 1943, Los Angeles suffered the first of its really bad air pollution pictures, and this picture is one illustrating someone with burning eyes in the smog of Los Angeles. This was 1943. It was in the midst of World War II. The industrial buildup of that era brought in a number of kinds of industry that had not been in the area before. There was a butadiene plant, artificial rubber plant, that was contributing dramatically to this. But the air pollution continued to get worse. Here's a picture from 1948 showing the downtown area of Los Angeles. Extreme air pollution. It continued to get worse up until the 60s. There were a number of simple things that were done. In both cases, there were some well-identified primary sources of particles being emitted directly to the air. So in London, what was going on in that period? It happened to be December. They had a high-pressure area set over London for about 5 days. The temperatures were very cold, around, minus 10, Celsius. It was quite cold. What do people do when it's cold? They turn up the heat. At that time, the homes in London were heated by burning soft coal. So they burned more coal. They dumped more particles and more sulfur into the air, and that was contributing to the air pollution. What's going on here in Los Angeles? Los Angeles is a special environment. It's got mountains that stop the airflow, so the air sits over the Los Angeles basin much longer than it does most other places, and it cooks. There were a lot of primary emissions. People in that era were burning their waste in backyard incinerators. So that was putting a pulse of smoke into the air every afternoon. They tried to alleviate that. They put in a law saying you couldn't burn till after 4 o'clock in the afternoon. So at precisely 4 o'clock every afternoon, the air would turn black. Everyone would light their incinerators when they could do it. But there were also growing numbers of automobiles. And the automobiles of that time did not have any kind of emission control and contributed dramatically to the air pollution. This is something that was gradually understood in later years, and controls were brought into play. The primary sources were relatively easy to address. In London, they banned the use of soft coal for heating. They went to burning charcoal or coke. In doing that, they solved the ground level emission. Then they built taller smokestacks on the factories and exported their air pollution. That was the genesis of the acid rain that followed in the 60s. We go to the modern era. We go to the present air pollution capital of the world. It's not Beijing, it's Delhi. They have far more extremely severe days than Beijing has. Again, major source of pollution is burning. But it's not all local burning. There's a huge, if we look down, here's Delhi, here's upwind of Delhi. Each of those red dots is a fire where they're clearing the stubble in the agricultural fields. This biomass burning is producing this huge plume of smoke that's contributing to the Delhi air pollution. Now, that's not the only source. There's a lot of local burning for cooking, for waste disposal and other things, plus automobiles and all of the other sources. There's a huge primary emission problem, but there may be some other things going on as well. Now, if we take a look at these two, just another nice picture of the sort of pollution that was making up the London smogs. Here's one index comparing the numbers of bad days, relatively good days to really bad days in Beijing versus Delhi over a 4-month period. It happens to be a 4-month period where the meteorology was not giving the really extremely bad days in Beijing, but was doing it in Delhi, and you have to suspect that there may be some selective data mining going on. But if you look at the long-term data, here's just over a few years in Beijing. This is the particulate air pollution. This upper line is 1,000 micrograms per cubic meter, a milligram per kilogram of air. That's a lot of particles in the air. And the concentrations are getting up there periodically over time, many days up at very hazardous levels. Now, these are megacities that are undergoing very rapid development. They're not the only places that have the air pollution problems. This is a recent picture from Paris, where Paris has had some episodes that have matched Beijing recently. And London has too. The air pollution problem is not going away. It's recurring. We need to understand it. And more than that, we need to develop the political will to address it. The technology exists to solve many of these problems. The political will to do it is ultimately the problem. And this is one of the real challenges that we all face as we think about how you address environmental issues. Solving the problems technologically is just the beginning. Somehow we have to communicate to the general population, and hopefully through them to the politicians, to actually get changes made that solve the problems. So, if we look at the most recent estimates, just last month, a report from the World Health Organization published some new estimates. This one is a little bit dated. It's from October last year, estimating that 7 million deaths globally were caused by air pollution in 2012. 7 million people dying as associated with air pollution. Now, many of these are in the third world. Many of these are due to indoor air pollution. And the people who suffer most from the extreme indoor air pollution in the third world are women who are cooking over fires in dwellings that don't even have a proper chimney, don't have a proper exhaust for the smoke. And so they're sitting in that smoke, taking care of their children, cooking the meals. The men tend to be outdoors and not suffering that same pollution. These problems, many of them are addressable. The question is, how do we make it happen? Now, what do we know about the health effects? Here we turn to a class of medical researchers known as epidemiologists, people who study the biological statistics of health. And this is a classic study, the so-called six-city study by Pope and Jockey, that looked at the health effects of fine particle air pollution. Now, they focused in on particles small enough that when they're inhaled can penetrate through to the lower airways in the respiratory tract. Particles smaller than about 2.5 microns aerodynamic diameter. And what they show is that the mortality rate increases with the mass concentration of PM2.5. And it increases dramatically. So if you go from 10 micrograms per cubic meter, where they defined that as unity on this adjusted mortality risk scale, up to 30, you see about a 30% increase in the adjusted mortality rate. So about a 10% increase for, let's see, it'd be about a 10% increase for, well, let's say a 15% increase for 10 micrograms per cubic meter. That's a pretty substantial increase. Now, this is looking at the levels that we typically encounter in the US these days on annual average exposures. But remember, Beijing right now, the concentrations are going up in peaks to 1,000 micrograms per cubic meter, an annual average in the hundreds. These are huge concentrations. The health effects must be profound. Now, one of the first things people think about when they think about the health effects of air pollution is, oh, this is going to be a respiratory tract issue. Lung cancer, emphysema, other bronchitis, other respiratory diseases. But in fact, you do see lung cancer, you do see cardiopulmonary diseases, but you also see cardiovascular diseases. You see a reduction in heart rate variability. And that reduction in heart rate variability translates to things like heart attacks. So there are many, many factors that come into play, many ways that the particles affect human health. But of course, the question of how that occurs relates to how people receive a dose of these particles. And they do that by inhalation. When you inhale particles, some fraction of particles, the big ones, will deposit by inertial impaction in the upper airways. So you go down the respiratory tract. Eventually you get down to small enough scales that Brownian diffusion becomes important. If you look at the fraction of particles deposited as a function of particle size, you find that there's a large space in large size range where many of the particles that you inhale, you will exhale again. There's a peak at large sizes, which corresponds to those that deposit by inertial impaction. As you go down to very small sizes, you find that the deposition becomes very efficient. But at the smallest sizes, you discover that substantial amounts deposit even in the upper airways. The smallest particles diffuse so fast they can deposit in the nose. And if they deposit in the nose, they deposit on the olfactory mucosa. The olfactory mucosa, they can translocate into the olfactory neurons. Then they migrate up those neurons at a relatively high velocity over a very short distance, a few centimeters, and they can go into the olfactory cortex. And you have now metallic nanoparticles getting into the brain without having to cross the blood-brain barrier. So many different mechanisms, and I can't go through those. I'm not an expert in those, but critical issue here is particle size is important. The small particles are important. PM 2.5, measuring the mass of particles down here, really does a pretty poor job of estimating what's going on here. We don't really know what are the exposures to the smaller particles that are likely the part of the aerosol that is driving these health effects. I've talked about the problem as though it's a big area problem. But if we look at some special locations, like along a roadway, this is a freeway coming out of the harbors in Los Angeles that's bringing in the goods coming largely from Asia, being transported by truck through the LA basin, huge truck traffic. If we look at the concentration of ultrafine particles, here particles 25 to 50 nanometers, here 6 to 25 nanometers. We see that concentration is huge right at the roadway, dropping off dramatically within a few hundred meters of the road. That's daytime. Nighttime, it's a little different. Daytime, there's a lot of mixing going on. Nighttime, the atmosphere is more stable. Recent work from Suzanne Paulson at UCLA shows that that effect extends out maybe to 1,000 meters or so. This is Los Angeles, where the terrain is relatively open. What's going on in the urban canyons in Hong Kong? This is a question that needs to be answered. And to answer that, we've actually got to get data that's looking at these very short length scales. Now, do these have any effect? Well, this is just one study that illustrates an effect. This is the asthma probability as a function of distance from the roadway. This is from the group at USC, some epidemiologists who were studying the effects of that particular roadway, among others. And what we see is that the incidence of asthma doubles if you live within, if a child lives within a couple hundred meters of the road. This is a huge effect. It's a huge population that's being affected by that. So these are some of the effects we'd like to understand. But what are we doing to understand it? Well, we go out and we make measurements. But this is the map of the Los Angeles basin. This is an area of about 6,000 square kilometers that is the Los Angeles urban area. And each of those circles is one of the air quality measurement stations for the LA basin. So we have 6,000 square kilometers we're trying to cover. We know that some of the concentrations that are important vary dramatically over a length scale of 100 meters, and we have a grand total of 40 air pollution measurement stations that are used to map this out. Not only that, 30 stations are equipped to measure ozone, 26 are equipped to measure CO, 25 to measure NO2, 11 to measure PM10, and 9 can measure PM2.5. And they're all strategically located to skip the local effects that I referred to on the roads. They're very carefully designed to avoid that. Why? At the time when those stations were first set up, there was not knowledge of these localized effects. They wanted to get data that were representative of the overall air quality, and so they tried to avoid the local concentration effects. It was a rational decision given the information available at the time. But it's an inadequate approach today. So we really need to think about new ways to address this. So presently, we've got the routine monitoring networks. They can give anywhere from long-term to hourly exposure, but they miss these local effects. We can go out and do other kinds of measurements. As researchers, we can go out and do intensive studies, the supersite studies. You have one here on campus. You have a super site that's equipped with a massive array of state-of-the-art instruments that can provide tremendous information, but at one point in space. And I must say, fairly far removed from some of the urban locations that one might be concerned about. This could provide fundamental understanding, but it can't map the exposure. We don't have enough spatial resolution to do that. We can't afford to put enough super sites out there to really map what's going on. Somehow, we've got to think of alternate ways to make the measurements. We can do this. We can try to do intensive but short time duration spatially resolved measurements. And I'm going to focus the rest of this talk on one such measurement campaign, a campaign called CalNex. So CalNex, or California Nexus, was really designed to give research at the nexus of understanding air quality and climate change. I will focus strictly on the air quality part of that. The climate change issues are every bit as important, but there's a limited amount of time, so I'll focus on the climate change. And there have been quite a few people involved in doing this. I will talk about one platform, one aircraft that we've been using for making measurements, trying to map what's going on in the Los Angeles basin, and the kind of picture that we're beginning to pull together from that. This was 1 out of 5 aircraft, 2 ships probing off the coast, 1 major ground station in the Los Angeles basin, another one in the San Joaquin Valley, the Central Valley of California, all probing this, probably about 400 researchers involved. We had 5 groups represented on this one little aircraft. And with this, we went out and we probed the LA basin. Now this is looking at the LA basin right near downtown Los Angeles. You see we have some rather pronounced hills, but it's relatively flat. Here's the center of Los Angeles. You can see all those high rises. It's actually a very small number of high rises compared to what you have here. It's a relatively open terrain. This is a moderately polluted day. The center of the city is about 16 kilometers from where the aircraft was at this point. So we're looking through 16 kilometers of smog at this point. This is at the other end of the basin. Here we see the mountains. These mountains rise up to this range. Here is about 2,000 meters. That peak's about 3,000 meters. Here we see the pollution leaking out of the basin over this mountain pass. And we'll see this pass again and again in the course of this talk because we flew through that pass on numerous occasions. We set up an experiment. This was a huge experiment trying to understand the origin and composition of the Los Angeles aerosol, how it ages, how it affects potential cloud droplet formation. I won't talk about that. The mixing state, and the nature of the aerosol particles, the role of black carbon, and ultimately, from the climate change perspective, the radiative implications. To do this, we take our laboratory to the air. Our laboratory is this Twin Otter research aircraft. This is a rather heavily instrumented aircraft. It's got a long sampling probe that's bringing sample into the cockpit or into the fuselage where we have a lot of instruments. There are also wing pods on the aircraft where we have additional instruments mounted. If we look into the aircraft, here we see a bunch of people getting their instruments ready to fly. As we're getting ready to fly, everybody's there working on their own instrument. When the aircraft takes off, they all get out. One scientist is in the back running all of the instruments, about 20 to 30 different instruments, one person responsible. All those instruments have to be properly designed and built and operating in a way that doesn't require a lot of personal attention because the flight scientist is focusing mainly on the science, and we'll see some examples of that. This is one of the bigger instruments. You have an aerosol mass spectrometer. This is loading it into the aircraft. We take it off the aircraft at the end of every day so that we can keep it under vacuum to maintain the data quality. That is no small task. It's a 400-pound instrument that we're putting on. And of course, we have the graduate student who's putting the instrument on with 2 of the aircraft mechanics supervising her operation. But they did allow her to do the work. We had a huge battery of instruments. And I'm not going to go through the whole shopping list of instruments. Those of you who know what they are can read these quickly. We have the standard instruments for doing the aerosol composition, for getting some optical properties, for getting some of the hygroscopic behavior, and for getting physical properties of the aerosol. So we have a very well-equipped aircraft and several copies of a number of these instruments to make it possible to capture things in real time. And then, why do we put these on an aircraft? Well, we want to understand what's happening throughout the region. And so what we do is we take off. We were based out here in Ontario, and we would fly through the basin. We had to fly specific routes because we have to deal with air traffic control. We had a ground site for this study at the Caltech campus right here, and so that became a corner in the standard flight paths. Down here we have one of the major source regions where we have the harbor, and we also have refinery operations. We have downtown Los Angeles here, and then we have some downwind areas. We have the Central Valley of California that we've probed, the San Joaquin Valley. We flew out over the Mojave Desert, out in this direction, and out through that mountain pass right here into this southern valley where we were also probing the air quality. So what I'm going to do is just walk you through some of these flights, the kinds of things that we saw in them. Not trying to go through all the gory detail, but just to give you a picture of what you can begin to see. We were very interested in the particles in the atmosphere. And there's always a challenge. How do you represent the data? Here, what we've represented is the ratio of the concentration of ultrafine particles, the number of particles per cubic centimeter, below about 2.5, below about 1 micron, actually, but with instruments capable of going down to 3 nanometers. So they're really counting the very smallest particles, and then a particle that would only count the particles above 200 nanometers. So we take the ratio of those 2 concentrations. If it's bigger than 1, we're in a region where fresh particles are either being emitted directly to the air or they're forming in the atmosphere. Where it's less than 1, we're really dealing with, we could be dealing with a desert dust aerosol. More commonly, we're dealing with a very aged aerosol. So what do we see? We see down here in the harbor area, in the area along the major freeways near downtown Los Angeles, we see a source region. We see a lot of high ratios. As we go downwind, we see the particles growing. We see fewer of the ultrafine particles. So this is all downwind region. We have a few hot spots where we're forming new particles, but mostly we see the fine particles in the source regions and coarser particles coming in as we go downstream. Now, one of the source regions that we were very interested in is this region down near the harbor. So this is Long Beach Harbor. Wilmington is where one of the major refinery operations is. We wanted to probe that. This is very congested airspace. We had to work very tightly with air traffic control. What we would do is do what they call a touch and go, where you fly up toward an airport, you come down like you're going to land, you get just down to the surface and take off again. And with that, we could get a vertical profile that took us all the way down to the ground. Nowhere else could we do that. Everywhere else, we're restricted to 1,000 feet, 300 plus meters above the surface. But there, we could get right down to the surface. And so we did that. And so we did that many, many times. And you could see, in this region, we saw lots and lots of ultrafine particles. Why? You've got the ships with all the fuel they're burning just to keep their generators and equipment going. And they're burning clean fuel. They're not allowed to burn the heavy fuel they burn when they're out to sea. You've got the railroads with their diesel locomotives, and you've got all the trucks. Huge amount of truck traffic in this area, and so you have huge ultrafine particle emissions from all of that. So that's just looking at what's going on right near the source. Now, take a little closer look at the basin. The prevailing winds are going this way. So the freshly emitted particles here are being blown out on this way. That's why we see this red streak as we're going down this one valley. As we go further inland, we're not getting those directly emitted particles. We have some that are coming in along these north-south freeways, but this is one of the major truck traffic routes, and it's also downwind from the source. So we can begin to see some patterns. We're dealing not just with the emissions, we've got to deal with the local meteorology. As we go out to a slightly larger scale, here we go out over that mountain pass, and down here we see in what should be a relatively clean area, we're just getting that little bit of effluent from the LA basin that's blowing out here. We see new particle formation here, and then again way down here. These are evidence that new particles are being formed by homogeneous nucleation in the atmosphere. So the gas phase reactants are producing condensable materials that are forming new particles. So if we want to understand the air quality out in these regions, we're going to have to be able to explain that nucleation. Up here we have another nucleation event. Here we have the northern route for trucks leaving the LA basin. And so we have a major truck emission source out in this area. So that's just simple physical characterization. What about the chemistry? Well, the chemistry, we use a tool that a number of you, I think, are familiar with. We use an aerosol mass spectrometer. Initially, when we've used the aerosol mass spectrometer, it's a device that brings in a sample of particles, takes it through a gadget called an aerodynamic lens that produces a very fine beam of particles going into vacuum. We chop that beam to produce a pulse of particles coming in. The time those particles take to reach a little hot oven where they impact and evaporate is related to their velocity. When they come into the vacuum, the small particles can keep up with the gas molecules, so they come in at high velocity, speed of sound. The big particles, their inertia causes them to lag behind. And so they come through at lower velocities. And so they separate in time when they reach this detector. Originally, we used a quadrupole mass spectrometer, but we can do better than that. We can actually put in a high-resolution mass spectrometer, a triple reflectron time-of-flight mass spectrometer that allows us to get resolution now down well below 1 atomic mass unit, down to the point that we can identify the atoms involved in a particular molecule. And with that, we can get some detailed chemistry. So if we look just at the simple analysis that we could do with the quadrupole, we can identify hydrocarbon-like organic aerosols, aerosols that are primarily carbon and hydrogen. And we can see oxidized organic aerosols that have considerably more oxygen in them. We detect these according to their mass, to M over Z ratio, mass over atomic number, or over charge ratios. The 43 relates to the hydrocarbon-like. The 44 tells us about oxygen. But if we go in with the high-resolution mass spec, we can now begin to break those peaks apart and see contributions associated with the hydrocarbon-like molecules. But we also see some oxygenated and nitrogenated species coming in as well. So we can begin to differentiate much more when we start using the high-resolution mass spectrometer. So we're now flying the high-resolution mass spectrometer. With that, if we go back to some work from Jesse Kroll, we could see that we can map the oxidation state very clearly in terms of the M over Z44 signal in the mass spectrometer. And we can look at the many different classes of oxidized organics. So we do a lot of detailed factor analysis to try to unravel the different groups in the composition, in the molecules that are in the aerosol. One problem with the aerosol mass spectrometer is it gives us chemical indications. It does not tell us what the molecules are, because we have a soup. We have everything that's in those particles coming through simultaneously. So we don't have the pre-separation that you might have in an analytical chemistry, where you can put a gas chromatograph in front of the mass spectrometer or run two mass spectrometers in series and do an MS or an MS to the N. We don't have that capability for the kind of time response that we need when we're doing flight experiments. Nonetheless, we can get a lot of information about the oxidation state of the aerosol, and we can begin to map out what's going on in the aerosol. So this is just a look at the kinds of molecules that we're identifying that contribute to the oxidation state. As we go to the hydrocarbon-like aerosols, for them to get to low enough vapor pressure that they condense, they have to be pretty high molecular weight. We have some water-soluble organic compounds that span a pretty wide range. The aerosols from biomass burning tend to be slightly lower molecular weight. By the time we get to the very low volatility oxidized organics, the molecular weights can be quite small. So we're beginning to map out the range of compositions. And if we look at what we're seeing when we look around the world, we see that this fraction of the signal, that's this 44 mass peak, provides us with a reasonably good indication of the O to C atomic ratio, although there is a huge amount of scatter as we look at all the different locations. And this really has to do with the sources, the terrain, the chemistry, the meteorology. Many factors are coming into play here. For CalNex, we're looking at one region, but still we have a pretty wide variety of sources. So let's look at some of our flights. Here I have latitude versus longitude for different sites. Here's the Caltech site. This is that harbor site. This is where we were taking off, right about here. This top flight is the organic aerosol. The size of the signals indicates the number concentrations of particles. The color indicates the composition. So this is looking at the organics. We see big particles and a lot of organics throughout the LA basin. If we look at the nitrates, we see that the nitrates are disappearing when we get out into the desert where it's really hot and the ammonium nitrate will evaporate. We don't have much nitrate down near the source region. If we look at the sulfate, we see a huge amount of sulfur down in the source region. That's the ships. The refineries are quite clean, but the ships are anything but clean, even though they're burning much cleaner fuel than they would normally burn. If we look at the ammonium, we see big pickup in the ammonium out in this region. Well, it turns out there's some dairy operations out in here. So those dairy operations are adding a lot of ammonia to the air in the downwind part of the LA basin. So we can begin to map out the chemistry. We can begin to see what's going on. I see I have a slide out of order, but as we look down, look at around the basin, we can begin to see how the aerosol is changing. We have one, this is looking at one flight. And I think I have this picture in here, but I seem to have put it out of order. There was a traffic accident and a gasoline tanker caught fire. So there was a big black plume, and we had a huge amount of black carbon in this region. Here we see, down at the Long Beach, we see a little bit of soot, actually a fair amount of soot. We see a lot of organic, the green. Sulfate is very high, that's the red. Nitrate, we see a little, and ammonium, we see a little. As we go inland, we see the nitrate is increasing, that's photochemistry taking place. We see the sulfate is decreasing, dilution with other things going into the aerosol. We see more organic coming into the aerosol, again due to photochemistry. And we see that the soot, the black carbon, is being maintained. Get out to Caltech, we have quite a bit of organic by this point, a lot less sulfur. We go far downwind in the basin, and we actually have a lot of nitrate, a fair amount of ammonium before we get out into the really hot regions of the basin. This is one snapshot, one flight. We can map out the oxygen to carbon ratio as a function of position in the basin. And what we see as we move from west to east in the Los Angeles basin, as we move downwind, the amount of oxygen in the aerosol is growing. So we're seeing dramatic aging of the aerosol. It's changing its chemistry. It's changing its hygroscopicity. It will act as a cloud condensation nucleus much easier downwind than it would in the upwind regions. If we look all over the basin at this oxygen to carbon ratio, we went up into the free troposphere a couple of points. We simply did a spiral up to high altitude and then back down again. Up in the free troposphere, we didn't see much oxidized organics. We had an oxygen to, I'm sorry, we saw a lot of oxidized organics, oxygen to carbon ratio up unity. Down in the basin, in the source regions, the levels were much lower. Just a few more slides to look at one other measurement. Another very important piece of the puzzle is soot, the black carbon. For that, we used an instrument called the single particle soot photometer. This is a laser-induced incandescence instrument where you use a high-power laser to zap a particle after you've detected it by scattering of visible light. The laser is so powerful that it causes anything that strongly absorbs to heat up the particle, ultimately to a point where it will glow brightly. It will be incandescent like a light bulb. And from the combination of the light scattering signal and the incandescence, we can get a picture of the behavior. So we have here the signals that we see. We have a scattering signal, this green signal. We have several different detectors for the light scattering. We have one split detector that gives us a threshold point that we use to define a start for firing the incandescence laser. And then here we see the incandescent signal, which comes in a bit later than the light scattering. From that delay, we can say something about how thick the coating is on the particle. So if we have a thick coating, it takes a while for the particle to heat up. If we have a thin coating, it can happen quite rapidly. So we have that window. And I'm going to skip that. As we look around the basin, here's the mass concentrations of black carbon. We have a few in these clean flights, a few spots where there's a fair amount along this freeway. This is a relatively clean episode with some high concentrations out here for reasons that I think I will have a picture to show. This is a more intermediate flight. Concentrations are higher. Different days, we saw very different behavior in this black carbon signal. We see here quite a bit more black carbon mass. And as we go to dirty days, we see some very high concentrations in several different regions around the basin. We can measure the size of the absorbing particles. And here we see something interesting. This is the LA basin. They're all pretty small, down around 130 to 140 nanometers. As we go out of the LA basin, Los Angeles basin, into the Central Valley of California, we start seeing the particles that contain the black carbon being quite a bit larger. They've aged. They've grown more. We don't see quite as much growth out here, but we still do see growth in the particles. We can look at the thickness of that coating. We see in the basin, most of the particles don't have a very thick coating. But as we go out of the basin, we start seeing, or in the downwind regions, we start seeing more with more condensed organics on top of the black carbon. And so we're beginning to map out what's going on as we move around the basin. So this is just one flight. You can get a picture. Here's the time lag, the percent of thickly coated. This is the black carbon mass. This is the size of the particles. So we see just dramatic differences. If I went through day by day, we would see dramatically different patterns. We can look also at this thick coating on the particles, on the soot particles. In another way, this is the volume equivalent diameter of the soot, of the black carbon that's absorbing the light, compared with the light scattering diameter. And so here we see down, this is Long Beach, this is in that source region by the harbor. We see the particles, black carbon, is a little bit smaller than the optical diameter. There's some coating on these particles. If we go further downwind, here, this is in the outflow regions, going out those canyons into the desert. We see that the particles have grown a fair amount. But we also see some that have grown a lot in particular regions. This suggests things are all pretty relative. This is the picture that I had put out of order. When we do these flight experiments, there are always targets of opportunity. This is where that student who's in the back of the airplane as the flight scientist has to make a judgment call. Do we continue on the flight plan that we had set up, or do we go after this? And I have to say, I'm very happy that the student said, we go after this. Let's document what's going on in this plume. So he took advantage of that, and we saw in that plume some really huge amounts of black carbon. That was that tanker fire. Most of the rest of the places was only a few percent of the aerosol, but we saw some rather dramatic effects. But these things happen, and they contribute to what's going on in the air. And you can't address the whole air quality problem unless you think about not just what happens every day, but what happens in the unusual event, because those can change the story dramatically. So just a few concluding comments. You know, this particulate air pollution, it's a recurring theme. It's not going away. We're going to have to deal with it for a long time. There's a bright future for people who are going to work to understand it and help solve it. And so I think I'm looking at a group of people here that are going to be contributing to that long beyond the time when I'm contributing actively to it. Primary emissions continue to be a major part, particularly in the developing areas. And they contribute much to the worst episodes. The black carbon, biomass burning, dust. These things can be understood. Many of them can be addressed directly. You could find other ways to clear stubble. You don't have to just burn the fields. There are many different ways to deal with these problems. The secondary aerosols are an important part as well. And you can't understand what's going on in the air unless you consider both. And they increase with age. The sulfates are part of that, but also we have to think about the secondary organic aerosols. So I've only just given a snapshot of one study. We need to do these studies for all of the different places where we're facing these problems. And we need to do them with enough resolution that we can identify the sources and then create the political will somehow to attack those sources. Find ways to do it economically. It doesn't require breaking the bank to solve air pollution. Los Angeles is much cleaner now than it was when I moved there not long after I completed my graduate studies, which is a long time ago, long before many of you were here. How's it been done? It's been done by using fundamental science, by using models of air quality, by collaborating with economists who think about what it costs to do things and devising ways to address the linkage between technology, economics, and air quality. Pulling all of that together has led to tools that people use for designing air quality strategies. People will model air pollution in a basin and say, what if I got rid of organic solvents in paint? If I got rid of organic solvents in paint, well, I can do that on the computer really cheap. Do the simulation. Hey, it makes a difference. Then you go back to the paint manufacturers and say, we'll help you, give you some money to get the organics out of your paint. But by the way, in 5 years, you can't have them there and sell your paint. Guess what? They got it out, and it really made a difference. You can do that with a lot of different sources, and that is being done. That's what's being done in California. It's what can be done in other places, and what really needs to be done to bring together the science and the policy sides to try to solve these really complex problems. So I've talked about work that involves a lot of people. It's the graduate students, the postdocs, who do the vast majority of the actual research. For the flight experiment, this is the crew from the CalNex experiment, the people who were involved in the flight experiments. That's my colleague, John Seinfeld, whose name I'm sure many of you know. Important people like the pilots who actually got us up in the air and got us around the basin safely and back. And a lot of very, very talented students and postdocs. This is more of our group in our new chamber facility where we study some of the fundamental reactions trying to unravel mechanisms. It takes a lot of different kinds of research, different kinds of measurements, modeling, all pulled together to solve these problems. And there are a lot of people depending upon you to do it. So go to it. Be happy to answer any questions. I'll stop there.
Thank you for Professor Flagan to give us this enlightening talk. On top of that, I'm really happy to hear Professor Flagan mention about how to solving air pollution issue. You have to work with a group of scientists, work with policymakers, environmental economists. That is the sort of thing we have been trying to do for the last few years, and we have been writing big proposal to the Hong Kong government. Unfortunately, the Hong Kong government are not listening. Hopefully, next time we'll get Professor Flagan in the RGC panel, and we may have better luck with that. And with that, the floor, I open the question to the floor. Anyone would like to ask some questions? Please.
Yes, I would like to ask, so you did these studies on the air quality in California. So compared to other regions in the world where they have similar industry or maybe similar ports, how do you think California is doing, and what is like currently your way forward to even more improve the situation?
I think, the industry in California, for the most part, is among the cleanest in the world. That the regulations can and do work, but it's not enough. The mountains that we have, which give us the very nice climate that we have there, which is a warm climate without the humidity. We have a cold ocean off the coast. It's very nice, but it also means that we have some really severe challenges. We have that long residence time in the air. There are probably some industries that should not be in Southern California. I must say, I seriously question whether Southern California should be promoting the harbors as part of the industry for the basin. Now that's politically an unsupportable viewpoint. But if you really wanted to clean up the air, getting rid of the harbor and the trucks that go with it would have a huge impact. If you can't do that, then you start asking what you would do as an alternative. Well, one is you put the ships on electricity when they're in the harbor. And you put the goods on electric trains to get them out of the basin. It doesn't make sense to ship goods by truck. Now again, is that politically viable? There are a lot of people who would be very unhappy with that proposal. We need to continue to focus in on all of the different sources. And it's one at a time. You identify a potential problem and you attack it. And that is being done. The shift from conventional gasoline automobiles towards hybrids and ultimately toward electric is coming. The faster it can come, the better. I would love to see the US start taxing gasoline at a rate like the rest of the world does, because that would have a huge benefit for that. But that is not going to happen in the near future, certainly not in the present political climate. I wish there was an easy answer. Technologically, there is. Politically, there's not. But this is where the communication is critical.
Maybe I would like to ask a question. This research, what kind of order funding you are talking about?
Are you planning to buy an airplane or not? So that airplane belongs to the US Navy. We set up a collaboration with the Naval Postgraduate School. The Navy has interest in understanding aerosols and clouds over the ocean. And so a lot of what we've done with this has been things that directly support that. For this particular study, NOAA funded the flights. For that flight series was about, trying to remember, was about 4 weeks. So that's probably $300,000 US just for the flight time. Add to that all the people and instruments. Those I think you can estimate much better. But you know, it's not cheap. There may be other ways to do it, but and you need to have the airspace to do it too. Doing that in LA Basin was very hard because of all of the commercial air traffic that we have to deal with. There were lots of places that we wanted to measure we couldn't. It's not cheap.
You raise a question when you're taking out this talk about actually most of the air quality stations we're looking at actually does not necessarily mapping the real exposure to human health.
Yep.
And you show the results from aircraft measurements. The aircraft are actually flying much more higher than those air quality stations. Nobody can actually breathe the air out there. So I would like to ask, how do you estimate or make this kind of implications from this type of measurements for the health?
We can only get the large, we're still limited to the large scale picture with these flight measurements. We can use, what we can do is use atmospheric modeling. So the measurements have to be coupled with the modeling. You can only make measurements with some finite spatial and temporal resolution. We can do a lot better than we've done before, than we're doing today, but there will always be some limits. To get to the questions of actual exposure and better yet dose, you know, what is actually deposited in the respiratory tract? That's what I want to know. To get there, we need to totally change the paradigm. We need to rethink how we are making measurements to understand the impact of air quality on human health. We need to think about how we monitor what an individual is actually exposed to. So I will do a workshop on aerosol measurement. A question I will pose, I will do it in two parts. One part is I will talk just about how the instruments that are out there work. And I will try to introduce the physics, the technology, the chemistry behind the different measurements. That's one part. And then for those of you who are really interested in the part that I think is going to be a lot of fun is to have a discussion about what it is we need to know without regard to what tools we have available to do it. And then start thinking about how you would create a new paradigm for measurement to get the information that you need to know to solve a problem you want to solve. I want to solve the problem of dose that individuals have throughout an urban airshed. I don't think we're going to do that with the present instruments. I don't think we can do it with $100,000 instruments. We certainly can't do it with $500,000 instruments. We need to think more about $100 instruments. We need to think about totally different ways to make the measurements. And there's a lot of opportunity there. And there's opportunity for business too. There's opportunity to, I don't think the present aerosol or air pollution instrument makers are going to build the instruments that are needed. I think it's going to be new startups that will actually do that. But I'd like to pose that question. It's a fantastic question. I wish we could do it with what we have now, but I don't think it's going to happen. I think we have to change the way we look at the science. And that will do some things that some of my colleagues think are absolutely crazy. I will actually say that we need to stop going after the highest possible quality of data, the highest resolution, and we have to think about what's good enough and practical and make it actually happen.
Presumably, you mentioned earlier you actually have one particular location, the aircraft actually flying down.
Yeah.
Right, so you do have the...
At that one location, yes.
That one location. That's still quite valuable.
And at one point, they happened to be able to do it right over the plume, right through the plume of one of the ships that was still operating under its engines. And so they were able to capture a snapshot, but just a few seconds, which unfortunately isn't long enough for some of our measurements to be complete. Yeah.
Does what you just said mean that you're going to move more into monitoring indoor air quality? Because as humans, we spend 80% of our time indoors.
That probably is part of it. Certainly, if you wanted to solve the major air pollution health problem in the third world, it's the indoor air quality in the huts that is the dominant issue. And there are some people who are actively pursuing that. They're using instruments that are not much more complex than a smoke detector to infer qualitative statistics on exposure. I think we can do a lot better than that, but they're getting useful information. So yeah, I think indoor is part of it.
Yeah, I've been reading about people using mobile phone to actually measure light using optical method to integrate that in mobile phone type of thing.
Okay.
Would that be something along the direction you're talking about?
It's one possibility. If you wanted to estimate PM 2.5, we can go back to techniques that people were using 20 and 30 years ago, where they were using the extinction coefficient with some semi-empirical or totally empirical formula to estimate PM 2.5 concentrations. What we could do is we could take the camera that's in that phone, throw the phone away. We don't need that complexity. We can do something much simpler. We'd use the webcam. You could imagine having a bunch of webcams strategically placed, or maybe not so strategically placed, taking pictures of the same thing all the time. Not trying to get a beautiful view, trying to get some good contrast that allows you to infer an optical density. And from that, you could get a distributed throughout an urban area with really pretty low cost and pretty high resolution. You could get an estimate of the PM 2.5 distribution. I don't think you'd get an estimate of the ultrafine particle exposure, but you could get that one parameter, and you could do it with a very, very simple technology. So sure, we can do that. We might be able to come up with sensors that we could attach to cell phones to acquire and transmit data. An example of what can be done is something that's been done in studying earthquakes. So, some of my colleagues who study earthquakes, seismologists, what they did is they took the accelerometer that's in your cell phone and they made a little module. It costs about $50 a piece. It has the accelerometer, it has a GPS chip, and it has a transmitter that will transmit to a local computer network. They're not going to the expense of having everyone be in a cell phone number. And they gave them away to people. So they're doing crowdsourced science. So now in the Los Angeles basin, 3 weeks ago, and then again about a week and a half ago, we had some significant ground motion, had some earthquakes. But now, instead of saying, we saw these accelerations at this point, they could see the waves sloshing back and forth through the basin. So they get a picture that you could model before that, but no one could afford to see it. But they can see it because they made these sensors. Now, suppose we could make a $100 particle sensor. You could take the price of a TSI SMPS, and for that, put 1,000 sensors out in the field. What could you do with that? Even if you don't have complete control over it. So yeah. That's why I'd like to think outside the box, why I think I'd like to sit down with a bunch of people who are trying to see where they're going in this science and talk about what might be. Not what is, not what we can do with the tools we have, but what we might dream of. Can we find new ways? And I'm sure we can. I have some ideas that I've conceived, but I suspect other people will come up with different ideas.
Any other questions? Okay, so good job. Thank you for Professor Flagan to give us very enlightening talk. Good job because today's, I just checked my iPhone, today's the air quality health index was not that brilliant, actually towards the high side. So good job we spent three hours here and listening to Professor Flagan. So with that, thank you again.